Here, in the Salzburg Alps, is one of the largest ice caves in the world. At 1,600 meters above sea level lies the Eisriesenwelt, a cave system 42 kilometers long. Today, only the first 500 meters are ice-bearing and a popular tourist attraction. In the past, there was much more ice here, even in the inner areas of the cave. Geologists at the University of Innsbruck can prove this with the help of special carbonate deposits. They can use cryogenic cave carbonates to reconstruct the partly unexplained climatic history of the cave and the formation of the ice. The data can also contribute to a better understanding of today's climate change. Christoph Spötl and Gabriella Koltai are on their way to the cave entrance. The Eisriesenwelt is located above Werfen on the edge of the Tenin Mountains in the Austrian province of Salzburg. As quaternary geologists, they are dedicated to the last 2.6 million years, a climatically dynamic period with several ice ages. Until about 20,000 years ago, ice masses, some kilometers thick, profoundly altered the Alps. When the Ice Age glaciers plowed the Salzburg Valley into the Alpine mountain range, part of what was probably originally a much larger cave system was eroded away, exposing the present-day entrance.
The Quaternary period is basically the last 2.6 million years of Earth history. It's not just any geological episode, but it's the most recent one. So when you walk on the mountains of the Alps, for instance, if you look in the valleys, you always see sediments and processes which have occurred in the most recent geological past, which is the Quaternary. We are geologists interested in climate or in the climate evolution. It's a very obvious question: why did Earth undergo certain changes in the most recent, say, hundreds of thousands of years?
The cave is much older, probably several millions of years. Since the temperature in the first few hundred meters of the cave does not rise above 0 degrees all year round, penetrating water can form massive ice structures. The latest laser scan surveys show that the ice covers an area of about 11,000 square meters and has a volume of several 10,000 cubic meters. The rest of the cave is a little too warm, at just above freezing.
So in this particular cave, we follow the ice on the time scale, basically. We see the ice today, we can study the ice, it's several meters thick in some places. So in this case, we are almost glaciologists, but we are geologists, so we try to learn from people working on ice deposits, because this is a very specialized deposit. It's not commonly studied, it's a neglected one. It's a glacier that never sees the sun and has a very special dynamics. It's hardly understood. And this is a very interesting question, a very challenging one, I have to say. At the same time, in the interior part, we see no ice today. There may be a little bit of ice in the winter, but it's usually plus degrees. Right here, it's plus 1.5 roughly where I'm standing. But we do see clear evidence that there was ice in the past, and not just a little bit, but quite extensive ice extent. So it's like a time journey to some extent, yeah.
The ice is sampled so that, for instance, conclusions can be drawn later in the laboratory about its formation and age. The age range of the ice deposits is wide. In addition to more recent ice formations, there is ice from the Middle Ages, for example, and at the base of particularly thick formations, the ice is as old as about 5,000 years.
The key question is always, how old is the ice, or how old was the ice? When was the ice there? When did it go away? And for that, in the ice, this is a special ice. It's not formed from snow, as a glacier is formed. It's formed from water, freezing water. So it's usually very clean, which is very difficult to study. It's basically just water ice. And we still look for organic impurities, small organic remains. And this can be dated using radiocarbon, which is a well-established technique.
In today's inner areas of the extensive cave system, geologists find special cave minerals. They are called cryogenic cave carbonates, CCC for short. These small crystal aggregates only form when water dripping from the ceiling of a cave chamber slowly freezes on a substrate of cave ice. CCC, therefore, allowed to map the extent of ice also in deeper parts of this cave system that today are too warm for ice. In addition, CCC can be dated and provide accurate information when these climatically colder periods occurred in the past.
On this block you can see several cryogenic cave carbonates, in short CCCs. You can see many examples of these and they form in ice. So at the time when these carbonates were forming, we had a huge ice in this room inside the cave, and there was some water dripping, which created some pools in the ice, and these water pools were freezing very, very slowly, and in these water pools these CCCs were precipitating. And if we look at them, you can see that the inner core is dark brown, and then they have a white outer surface. And we are studying these CCCs because they are very good indicators of past permafrost thawing events, and we can define the timing of their formation very precisely.
The researchers take samples of these rare cave minerals. Temperature and carbon dioxide measuring devices are read out and provide precise data on today's microclimatic conditions in the cave. The analysis of the cave mineral samples takes place at the Institute of Geology in Innsbruck.
To define whether these crystals formed in ice, we use stable isotope analysis. We analyze the stable carbon and oxygen isotope values of these crystals, and to tell the age of the crystals we use uranium-thorium dating. We cannot do this in Innsbruck. We do the first preparation steps here, so we drill the sample and prepare them for chemical analysis that we either do in China or in the USA. We also analyze these water samples for their, the ice samples for their stable isotope composition, in this case oxygen and hydrogen, and we do this with a different machine at the moment. We would like to know whether we can see any climate signal, for example, in this ice, whether there is a change in these isotope values and why these changes could be.
They can distinguish 6 generations of CCC, which indicates 6 different glaciation phases in the cave. The oldest CCC are about 75,000 years old, while the last time that the inner cave parts contained extensive ice was about 12,000 years ago. The data collected by geologists here and in many other caves worldwide clearly reveal one common theme: climate change. More specifically, that the rate of change in recent decades has accelerated. This can be seen rather dramatically on alpine glaciers, but also in many alpine caves, the ice is disappearing rapidly. Eisriesenwelt, thanks to its very large dimension, still buffers this atmospheric warming. What exactly climate change means for the ice in the underground of the Alps, further research or time will tell.